Hello, friend. Welcome to Science for Sleep. Whether you're returning tonight or just finding this channel for the first time, this is a quiet place to slow down, learn something gentle, and let the day gradually fall away. Tonight, we are drifting toward the ocean. Not into a storm, not into danger, but toward the soft, steady sound of waves moving across the shore. That sound is one of the most familiar sounds on Earth. A wave rises, folds over, and spreads into white foam. The water rushes up the sand in a thin silver sheet. Then it slows, thins out, and slides back toward the sea. For many people, that rhythm feels calming almost right away. It gives the mind something simple to follow. A crash, a pause, a soft pull backward. Then another wave arriving in its own time. Part of that relaxing sound comes from water tumbling over itself. Part comes from millions of tiny air bubbles trapped inside the foam. As those bubbles form, stretch, and pop, they make a soft fizzing sound. And part of it comes from sand and small stones being gently moved back and forth by the wash of water. So even the peaceful sound of waves is not one sound at all. It is a quiet mixture of water, air, gravity, bubbles, sand, and motion. The ocean covers about 71% of Earth's surface. That means most of our planet is wrapped in water. And wherever wind touches that water, waves can begin. Some waves are no taller than a few centimeters. Others rise higher than houses. Some last only a few seconds. Others travel across whole oceans long after the storm that made them has disappeared. If you enjoy these quiet journeys, you're welcome to subscribe. And if it feels natural, to leave a comment sharing where you're listening from tonight. It helps others find their way to this calm corner of the world, one sleepy traveler at a time. Most of the time, we do not think of waves as a science topic. We think of them as background. They are the sound in a beach video, the moving blue lines in a painting, the gentle white edge where the sea meets the land. But every wave is a real physical event. It has a shape. It has a speed. It has energy. It has a reason for forming. A wave is not just water moving forward like a wall. In many ocean waves, the water mostly rises and falls in place while the energy moves onward. A floating leaf or piece of driftwood may lift up, sink down, and lift again as a wave passes under it. It may drift slowly, but it does not shoot forward as fast as the wave itself. That simple detail tells us something important. The wave is not only the water. The wave is the pattern moving through the water. It is like a ripple crossing a blanket when someone shakes one edge. The blanket does not fly across the room. The shape moves through it. Ocean waves work in a similar way, though the ocean is much larger, deeper, and more complex. Wind pushes on the surface. Gravity pulls the lifted water back down. The water responds by rising, falling, folding, spreading, and settling. Over time, with enough wind and enough open distance, tiny ripples can become rolling swells. Those swells can travel for thousands of miles. A wave reaching a quiet beach at night may have begun far away, under a different sky, in weather no one on that beach ever saw. That is part of what makes waves so fascinating. They feel close and familiar, yet they connect the shore beneath your feet to winds far out at sea. They connect the sound beside you to storms beyond the horizon. They connect the simple act of listening to one of the oldest movements on the planet. And as the water keeps arriving, one soft line after another, the ocean begins to feel less like a flat surface and more like a living system of energy. A system shaped by air above it, gravity beneath it, the seafloor below it, and the long open spaces between continents. So tonight, as the sound of waves settles into the background, we can follow that motion gently. We can begin with the peaceful crash at the shore, then slowly look beneath it, because inside that familiar sound is a hidden science of movement, distance, force, and rhythm. The wave comes in, the foam spreads, the bubbles fade, the water returns, and behind each small motion, the whole ocean is quietly at work. That quiet work begins with something that almost feels surprising. A wave is not usually a wall of water traveling across the sea. It can look that way from shore. A blue ridge lifts in the distance. The ridge comes closer. Then it rises, curls, and breaks. To the eye, it seems as if the same water has marched all the way from the horizon to the beach. But in most ordinary ocean waves, that is not what happens. The wave moves forward. The energy moves forward. But the water itself mostly moves up, down, forward, and back in small looping paths. A simple way to picture this is to imagine a cork floating on the surface. When a smooth wave passes under it, the cork does not race forward with the wave crest. It lifts, it tilts, it drops. Then it returns close to where it began. It may drift a little because of wind or surface current, but it does not move across the water as fast as the wave shape does. The visible wave is the pattern. The water is the material the pattern moves through. This is a little like a wave passing through a long rope. If someone lifts one end of the rope and sends a ripple through it, the ripple travels down the rope. But each piece of rope mostly moves up and down. The rope does not leave the person's hand and fly across the room. Ocean water works differently from rope, of course, because it is liquid. But the idea is similar enough to hold gently in the mind. The motion passes through the water. The water carries the motion without becoming the whole moving object. Scientists sometimes describe this as energy traveling through a medium. The medium is the substance the wave moves through. For ocean waves, the medium is water. For sound waves, the medium is often air. When you hear a wave crash, the sound reaches you, because tiny changes in air pressure travel outward from the shore. The air molecules vibrate back and forth. They do not fly all the way from the foam to your ear. The pattern moves. The energy moves. The molecules mostly shift in place. Water waves follow that same quiet rule in their own visible way. Beneath a gentle surface wave, bits of water move in rounded loops. Near the surface, those loops are wider. Deeper down, the motion becomes smaller. This is why a storm can make the surface wild while deeper water remains much calmer. A small fish several meters below a mild swell may feel far less motion than a seabird floating above it. The surface is where the wave shows itself most clearly. That is where the water lifts into crests and sinks into troughs. A crest is the high part of a wave. A trough is the low part between two crests. As each crest passes, the water below is not being permanently carried away. It is being moved, lifted, and returned by energy passing through. This is why waves can cross huge distances without needing to transport the entire ocean forward. A storm far offshore can press energy into the sea. That energy can travel outward in spreading lines. Hours or days later, the wave pattern can arrive at a coastline. The actual water touching the sand did not travel all the way from the storm. It is local water responding to energy that has reached it. This makes the shore feel even more connected to the open ocean. The foam at your feet may be made of nearby water, but the motion inside it may have begun far away. A gust of wind may have pushed the surface hundreds or thousands of kilometers from land. The water there rose and fell. Then nearby water rose and fell. Then more water rose and fell after that. The energy passed along, almost like a message carried from one patch of sea to another. That is the hidden beauty inside an ordinary wave. It is not only an object, it is an event. It is not only water, it is water carrying motion. And once that becomes clear, the ocean looks different. The surface no longer seems like a sheet being pushed toward land. It becomes a wide field of moving energy, with each rise and fall passing something onward. The wave arrives. The water lifts. The pattern continues. And somewhere behind that pattern, something had to begin the motion in the first place. The motion begins in the quiet meeting place between air and water. Above the ocean, the wind moves. Below it, the sea waits. At first, if the water is perfectly smooth, the wind has very little to hold on to. A glassy surface lets air slide over it more easily. But the ocean is rarely glassy for long. Even a light breeze can press against the surface with tiny, uneven pushes. The air does not grab the water like a hand. It drags across it through friction. Friction is the resistance that happens when two things rub or slide past each other. You can feel it when your hand moves across fabric. You can see it when wind brushes across tall grass and makes the blades lean. Over the ocean, that same kind of contact happens between moving air and the upper skin of the sea. The first result is not a large wave. It is a small wrinkle, a ripple. These early ripples may be only a few millimeters high. They are sometimes called capillary waves. The word capillary means they are shaped partly by surface tension, the thin, stretchy force that makes water behave as if it has a delicate skin. Surface tension is why tiny insects can stand on still water. It is also why the first ripples are so small and fine, like soft lines drawn across blue glass. But those little ripples matter. Once the sea is no longer smooth, the wind has more texture to push against. A flat surface is slippery. A rippled surface has tiny slopes and edges. Now the moving air can press harder on one side of each ripple. The ripple lifts a little more. Then the wind catches it again. The surface grows rougher. And with each bit of roughness, the wind finds more places to add energy. This is how the ocean begins to build itself upward. Not all at once, not with one dramatic motion, but through many small touches repeated again and again. A breeze of only a few knots may create soft cat's paw patterns on the water. Those dark, shivering patches sailors notice when wind first arrives. At around 4 to 6 knots, small ripples can cover the surface. At stronger speeds, the ripples grow into little wavelets, then short, choppy waves. On the Beaufort scale, an old wind scale first developed in the early 1800s by British naval officer Francis Beaufort, these changes were described by what sailors could see on the sea. Calm water looked like a mirror. A light breeze made ripples. A fresh breeze made small waves with white foam beginning to appear. The scale was practical because sailors needed to read the water before instruments became common. The ocean surface was a kind of message. The shape of the waves told them what the wind was doing. And the same idea is still true. Look closely at open water, and the wind becomes visible. Not as air itself, but as marks left behind. Dark patches, silver streaks, small peaks, lines of foam. A wave is one way the invisible air writes itself onto the sea. The rougher the water becomes, the more energy it can receive. This creates a gentle kind of feedback. Wind makes ripples. Ripples give the wind a better grip. The better grip lets the wind make larger waves. Then larger waves offer even more surface for the wind to push. Gravity also joins the process. When the wind lifts part of the water, gravity pulls it back down. That pull helps create the rising and falling motion that becomes a true wave. So every ordinary wind wave is shaped by two partners. Wind gives the push. Gravity gives the pull back. Together, they turn a flat surface into motion. Still, many small ripples disappear quickly. A breeze may pass over a pond, wrinkle the surface for a moment, and then leave it smooth again. The first waves are fragile. They need time. They need steady wind. They need open space. A small ripple can fade before it becomes anything more. But when the wind keeps blowing and the water stretches far enough ahead, that tiny wrinkle can begin a much longer journey. That longer journey depends on three quiet conditions working together: the strength of the wind, the length of time it blows, and the distance it travels across open water. That distance is called fetch. Fetch simply means the stretch of water the wind can blow over without being stopped by land. A small lake may have only a few kilometers of fetch. A wide ocean can give the wind hundreds or even thousands of kilometers to work with. This is why the same breeze can make very different waves in different places. Over a backyard pond, a short gust may ruffle the surface for a few seconds. The water becomes wrinkled. Tiny wavelets move outward. Then the motion fades against the shore. But over the North Atlantic, the South Pacific, or the wide southern ocean around Antarctica, wind can blow over open water for a very long distance. There are no trees to slow it, no hills to break it, no buildings to block it. Only air moving over water, again and again, adding energy one small push at a time. Wind speed is the first ingredient. A gentle breeze around 5 knots may only make small ripples. A stronger wind around 20 knots can raise rougher waves with whitecaps. Whitecaps are the little white breaking tops that appear when waves become steep enough for air to mix into the water. At gale force, around 34 knots or more, the sea becomes much more serious. Waves grow larger, foam streaks across the surface, and the ocean starts to look less like a patterned sheet and more like a moving landscape of hills. But speed alone is not enough. A powerful gust that lasts only a minute does not have time to build a large sea. It may slap the surface, scatter a few rough waves, and then disappear. For waves to grow, the wind must keep blowing. This is wind duration, the second ingredient. A steady wind over several hours can build a stronger wave field than a brief blast of stronger wind. The ocean needs repetition. Push after push, crest after crest. Small motion becoming larger motion. Storms do this very well because their winds can last for many hours or even days. Inside a large storm system, air may spiral around a low-pressure center, pressing on the sea over and over. The longer that pressure continues, the more energy the water can receive. The third ingredient is fetch. Even strong, long-lasting wind cannot build its largest possible waves if it runs out of open water. A storm blowing across a narrow bay may produce rough chop, but the waves are limited by the shoreline. The wind reaches land and the growth stops. Over the open ocean, the same wind has much more room. It can keep pushing the same moving wave field farther and farther. The waves become longer. Their crests spread apart. Their energy reaches deeper into the water. This is why ocean waves can grow so much larger than waves in lakes, even when the wind feels similar. A short gust over a pond makes small, busy ripples. A strong wind over hundreds of miles of ocean can build rolling waves taller than a person. In major storms, significant wave heights can reach 10 meters or more. Significant wave height means the average height of the highest 1/3 of waves, not the single largest wave. So if the significant wave height is 10 meters, some individual waves may be even higher. This matters because the ocean is not perfectly even. It is made of many waves layered together. Some are small, some are large. Some meet and briefly combine. A sailor looking across stormwater is not seeing one simple wave train. They are seeing the result of wind speed, time, and distance all written into the sea at once. The same wind can make a restless surface in one place and a powerful swell in another. It all depends on how long the wind blows, how fast it moves, and how much open water lies beneath it. So the tiny ripple from earlier is only the beginning. Given enough room, enough time, and enough moving air, that ripple can join a wider field of motion. The storm gives its energy to the sea. The sea holds it for a while. And even after the wind begins to weaken, the water does not forget right away. Even after the wind weakens, the motion it created can keep traveling outward. A storm may move on. The clouds may break apart. The sky above that part of the ocean may clear. But the waves that form there can continue spreading across the sea for hours, days, and sometimes much longer. This is one of the quiet wonders of ocean waves. They can outlive the weather that made them. A patch of stormy water in the North Pacific can send waves toward Hawaii. A storm in the Southern Ocean can send long, rolling swell towards South Africa, Australia, or the west coast of South America. The energy does not need the storm to stay with it. Once the wave pattern has formed, it can keep moving through the water like a message passed from one place to the next. Not every wave travels equally well. Short, choppy waves fade faster. They are crowded together, steep and messy. They lose energy more quickly because their little crests break, rub against nearby waves, and scatter into foam and surface motion. Longer waves behave differently. They have more space between crests. They rise and fall with a slower rhythm. And because their energy reaches deeper into the water, they can travel much farther before fading. This is where wave period becomes important. Wave period means the number of seconds between one crest and the next as they pass a fixed point. At the beach, a short period wave might arrive every 5 or 6 seconds. A longer swell might arrive every 12, 15, or even 20 seconds. That slower spacing is not just a rhythm. It is a sign of deeper, more organized energy. In deep water, longer period waves also move faster. A swell with a period of 15 seconds can carry its energy at roughly 40 kilometers per hour. A 20-second swell can move even faster. Over a full day, that motion can cover hundreds of kilometers. Over several days, it can cross a large part of an ocean basin. This is why surfers, sailors, and coastal forecasters often care so much about swell period. Two waves can have the same height, but feel very different. A 1-meter wave arriving every 5 seconds may feel short and bumpy. A 1-meter swell arriving every 16 seconds can feel smoother, heavier, and more powerful when it reaches shallow water. The height is only part of the story. The timing tells us how much energy the wave may be carrying beneath the surface. As storm waves move away from the storm, they also begin to sort themselves. The longer, faster waves run ahead. The shorter, slower waves fall behind. What began as a rough, confused sea becomes more orderly with distance. The ocean gently separates the storm's motion into cleaner lines. Far from the storm, the waves may no longer look violent. They may become smooth even and widely spaced. This organized motion is called swell. From shore, swell can look peaceful. A set of rounded waves lifts the horizon. The crests approach in slow order. The water rises, lowers, and rises again. Yet that calm rhythm may have begun in fierce winds far away, where the sea surface was covered in foam and spray. A beach can receive this energy with no storm clouds overhead. The sun may be setting softly. The air may be warm. The trees near the shore may barely move. And still, wave after wave may arrive from a storm hundreds or thousands of kilometers away. This is why the ocean can feel local and distant at the same time. The water touching the sand belongs to the shoreline, but the pattern moving through it may belong to a storm beyond the horizon. In that way, every swell carries a little history. Not history written in words, but in spacing, height, direction, and rhythm. The ocean records what the wind did. It keeps the shape for a while. Then it delivers that motion to places the storm never reached. So when a wave slides toward shore on a quiet evening, it may not be telling the story of the weather overhead. It may be carrying the last calm trace of a storm that has already disappeared. That last calm trace is what sailors and surfers call swell. Swell is not the messy water inside the storm itself. It is what remains after the storm has given its energy to the ocean, and the waves have traveled away from the place where they were born. Inside a storm, the sea can look confused. Short waves cross over longer ones. Crests break in different directions. Foam is torn sideways by wind. The surface may look like crumpled metal, always lifting, collapsing, and rearranging itself. But as those waves leave the storm area, the ocean begins to sort them. The longer waves move faster. The shorter waves lag behind. The cleaner wave lines spread outward. Bit by bit, the wild surface becomes more orderly. This is why swell often looks so smooth compared with local chop. Local chop is made by nearby wind. It is short, steep, and close together. On a windy lake or harbor, chop can make the surface look busy and restless, with little peaks slapping against each other every few seconds. Swell feels different. The crests are more widely spaced. The rise is slower. The fall is smoother. Instead of a quick slap, swell feels like a long breath moving through the sea. A small boat in chop may bump and shake as each short wave hits the hull. The same boat in long swell may lift gently, pause near the top, then settle down the back of the wave. The motion can feel calmer, even when the swell is carrying more energy. That is because the energy is spread through a longer, deeper motion. Some ocean swells have wavelengths of more than 100 meters. A wavelength is the distance from one crest to the next crest. In powerful, long-period swell, that distance can be several hundred meters, longer than many city blocks. The time between crests can also stretch out. A short local wave may arrive every 4 or 5 seconds. A strong open ocean swell may arrive every 14, 16, or 18 seconds. That slower timing gives swell its steady, spaced-out feeling. In deep water, longer period waves also travel faster than short period waves. A 15-second swell can send its energy across the ocean at around 40 kilometers per hour. Its individual crests may appear to move even faster, but the usable wave energy travels at about half that speed. In deep water. This is why a large storm can affect a coast days later. A storm near New Zealand can send swell toward islands in the Pacific. A storm in the North Atlantic can send swell toward Ireland, Portugal, or the eastern coast of North America. The waves do not need the storm to remain alive above them. The pattern has already been set into motion. The ocean simply carries it onward. This can make swell feel almost mysterious from the beach. The sky overhead may be blue. The flags may hang softly. There may be no strong wind nearby at all. And still, the water can rise in clean, powerful lines. To someone standing on shore, it may seem as if the sea has decided to move on its own. But the swell is not random. It is the organized memory of wind. It carries direction, timing, and energy from a distant patch of weather. Forecasters can often trace a swell back to the storm system that made it by looking at its direction and period. A swell arriving from the southwest points back towards storms in that direction. A longer period suggests a stronger or more distant source. The beach becomes the final page of a story that began far offshore. By the time swell reaches land, it may have crossed deep ocean for thousands of kilometers. Along the way, it has passed over water so deep that the seafloor had almost no effect on it. It has moved beneath open sky, past ships, birds, drifting seaweed, and dark water where sunlight fades into blue. And still, its shape remains clear enough to arrive as a set of smooth lines. This is the quiet order inside waves. They are not just high or low. They are long or short, fast or slow, close together or far apart, young and messy or old and organized by distance. To really see a swell, the eye has to notice more than the breaking foam. It has to notice the spacing between crests, the seconds between arrivals, the long rounded lift before the water falls again. Because the smoothness of swell comes from shape and timing. And once those details become visible, each wave begins to carry its own simple measurements across the sea. Those measurements begin with the shape that is easiest to see. The crest is the highest part of the wave. It is the lifted ridge, the bright line that catches sunlight first. The trough is the lowest part between two crests. It is the quieter dip, where the water settles before rising again. Wave height is the distance from the trough to the crest. If the trough is 1 meter below the average sea level, and the crest is 1 meter above it, the wave height is 2 meters. That number sounds simple, but on the ocean, it matters deeply. A 1 meter wave may feel gentle from a large ship. A 4 meter wave can lift and drop a small fishing boat with real force. A 10 meter sea can turn the surface into a moving field of steep water hills. But height is only one part of a wave's shape. Two waves can have the same height and feel completely different. A short, steep 2 meter wave can be rough and jarring. A long, smooth 2 meter swell can feel slow and rolling. The difference comes from spacing and timing. Wavelength is the distance from one crest to the next crest. On a small pond, that distance might be only a few centimeters. In coastal chop, it may be a few meters. In open ocean swell, the distance between crests can reach 100 meters, 200 meters, or even more. That means one wave can stretch longer than a football field before the next crest arrives. From the beach, this can be hard to see. The eye notices the white foam first. But farther offshore, before the wave breaks, the sea may be rising in long, rounded lines. Each line has a front slope, a crest, a back slope, and a trough behind it. Together, these parts create the wave's full shape. Wave period adds the rhythm. Period means the number of seconds between crests passing the same spot. If you stood safely on a pier and counted 8 seconds between one crest and the next, the wave period would be 8 seconds. If you counted 16 seconds, that would be a much longer period swell. The difference is not just musical. It changes how the wave behaves. A short period wave, around 5 or 6 seconds, is often made by nearby wind. It may feel busy and uneven. A long period wave, around 14 or 16 seconds, often comes from a distant storm. It can carry more organized energy, reach deeper into the water, and rise more strongly when it approaches shore. This is why surfers listen carefully to swell forecasts. A forecast that says 1.5 meters at 6 seconds does not mean the same thing as 1.5 meters at 16 seconds. The height is the same, but the longer period swell usually has more push behind it. It can bend around points of land, feel the seafloor earlier, and break with more power in shallow water. That power comes from the full wave, not just the part visible above the surface. A wave is not only the shining crest, it is a moving form with depth, width, timing, and stored energy. Even the steepness matters. Steepness compares wave height to wavelength. If a wave is tall but short from crest to crest, it becomes steep and unstable. If it is tall but spread over a long distance, it may roll smoothly for a long time. This is why the sea can look peaceful from far away, while still carrying great strength. A long swell does not need to be sharp to be powerful. Its energy is spread through a wider motion. The crest lifts slowly. The trough lowers gently. The whole surface breathes in long lines. And yet, hidden inside that slow shape is the memory of wind, distance, and time. A person watching from shore may see only the final white break. But before that break, the wave has already carried its measurements across deep water. Its height, its length, its period, its direction, its slope. Each detail tells part of the story. The ocean is not moving at random. It is shaped. It is timed. It is patterned by forces that can be read, measured, and understood. Still, the surface is only the beginning. The crest and trough are what the eye can follow. But beneath them, the water itself is also moving. And the deeper we look below that smooth passing shape, the more quietly complex the wave becomes. Below that smooth passing shape, the water is not still. It is moving in a quiet pattern the eye cannot see from shore. Near the surface, each small piece of water moves in a rounded path. It rises as the crest approaches. It tips forward slightly as the crest passes. It sinks as the trough arrives. Then it moves backward and returns close to where it began. This motion is often described as circular. In real ocean water, the circles are not always perfect. They can be stretched a little by wind, current, or nearby waves. But in deep water, the basic pattern is a loop. The wave moves forward across the sea. The water beneath it moves around and around in place. A floating seabird shows this gently. A gull resting on calm swell may lift upward, drift a little forward, settle downward, and then ease back. From a distance, it looks as if the bird is riding the breathing surface of the ocean. It is not being carried forward as fast as the wave itself. It is tracing the motion of the water under its body. The same thing happens below the surface. A tiny particle of water beneath the crest follows a loop. A particle a little deeper follows a smaller loop. Deeper still, the loop becomes smaller again. The motion fades with depth. This is one of the most important hidden facts about waves. The surface may rise and fall clearly, but the movement does not reach downward forever. In deep water waves, most of the motion is concentrated near the top. A useful rule is that wave motion becomes very small at a depth of about half the wavelength. So if a swell has a wavelength of 100 meters from crest to crest, its motion may become weak, around 50 meters below the surface. If the wavelength is 200 meters, the motion can reach deeper, perhaps close to 100 meters before fading. This is why long swell is not only wider on the surface, it also reaches farther down into the sea. A short, choppy wave may trouble only the upper few meters. A long ocean swell can move a much deeper layer of water. Still, even large surface waves are shallow compared with the full ocean. The average depth of the ocean is about 3,700 meters. The deepest part, in the Mariana Trench of the Western Pacific, reaches nearly 11,000 meters. A wave passing across the open Pacific may move water strongly near the surface, but far below, the deep ocean can remain almost untouched by that passing rise and fall. Down there, in cold darkness, the water does not lift with every surface crest. The wave is mostly a surface event. It is a pattern written across the upper ocean. This helps explain why submarines can sometimes avoid rough surface conditions by traveling deeper. Near the top, a storm may throw spray and foam into the air. Waves may heave and break, but below the wave zone, the motion softens. The water becomes steadier. The storm is still above, but its reach has faded. The wave's energy is real. It is powerful, but it is also layered. Strongest near the surface, weaker below, almost gone at enough depth. This hidden looping motion also helps explain why the sea can carry waves over great distances without sending all the water with them. The water does not need to travel across the ocean. It only needs to pass the motion along. One loop affects the next. One rise leads into the next rise. The shape continues forward, while the water mostly returns. It is a beautiful kind of balance. Movement without a long journey for each drop. Travel without the whole sea sliding sideways. Energy crossing distance through repeated local motion. From above, the wave may look like a single blue ridge. From below, it is more like a stack of fading circles. Large near the air, smaller with depth. Then quieter and quieter until the deep water barely notices. As long as the sea is deep enough, the wave can pass freely. Its lower loops fade before they ever meet the bottom. The seafloor remains far beneath, silent and untouched. But the ocean does not stay deep forever. Every wave that travels toward land eventually enters shallower water. And when those hidden loops begin to reach down far enough to feel the bottom, the wave must change. The wave begins to change before it ever reaches the sand. Far offshore, in deep water, its lower motion fades away before touching the seafloor. The wave can pass freely. Its rounded loops move beneath the surface, growing smaller with depth, never reaching anything solid below. But as the wave travels toward land, the ocean floor slowly rises beneath it. The water becomes shallower. The hidden loops under the wave begin to press closer to the bottom. At first, the change is gentle. There is no sudden wall, no sharp line where deep water ends. The seafloor may slope upward for kilometers, especially along wide continental shelves. Off the east coast of North America, for example, the continental shelf can stretch more than 100 kilometers from shore in some places. Along steep volcanic islands, the deep water may come much closer to land. The shape of the bottom matters because every wave responds to it, When the water depth becomes less than about half the wavelength, the wave starts to feel the seafloor. A wave with a 100-meter wavelength can begin changing when the water is about 50 meters deep. A longer swell with a 200-meter wavelength can feel the bottom even earlier, around 100 meters deep. This does not mean the wave touches the bottom like a solid object. It means the circular water motion below the wave begins to interact with the seafloor. The lower part of that motion is slowed by friction and pressure changes near the bottom. The base of the wave starts to drag. The top of the wave continues moving more freely, and the whole wave begins to adjust. This process is called shoaling. Shoaling means a wave is entering shallower water and changing shape because the bottom is affecting it. During shoaling, the wave slows down. Its wavelength becomes shorter, so the crests move closer together. And because the wave's energy is being squeezed into a smaller space, the wave height often increases. The wave begins to stand taller. From the beach, this is why a smooth swell far offshore can rise into a larger, steeper shape as it comes closer to land. The wave is not gaining new energy from nowhere. It is reorganizing the energy it already has. In deep water, that energy was spread through a long, smooth motion. In shallow water, the wave slows, compresses, and lifts. A calm blue line becomes a higher ridge. The slope grows sharper. The face of the wave becomes more visible. This is the moment surfers watch for. Far outside, the swell may look like a soft bump. As it reaches the right depth, over a sandbar, reef, or gently rising beach, the bump begins to steepen. The water draws up. The crest sharpens. The smooth traveling wave becomes something that may soon break. Different shorelines create different kinds of waves. A long, gently sloping sandy beach often produces spilling waves where the crest crumbles forward slowly in white foam. A steep beach can make waves that rise quickly and collapse harder. A coral reef can force a swell to stand up suddenly because the bottom changes depth so fast. This is why famous surf breaks often depend on very specific underwater shapes. The wave above the surface is being guided by land beneath the surface. Even if the seafloor is hidden, it is quietly shaping everything the water does. Shoaling also explains why waves arrive in sets near shore. As swells move through changing depths, some waves focus their energy more strongly than others. The ocean surface may appear to breathe in groups. A few larger waves arrive. Then a calmer pause follows. Then another set rises from farther out. To someone listening at night, this pattern may sound like the sea taking slow, uneven breaths. But beneath that peaceful rhythm, there is geometry, depth, slope, wavelength, friction, energy being pressed upward as the ocean floor rises. The wave has traveled freely across deep water. It has carried its pattern over distances that may span hundreds or thousands of kilometers. But near shore, freedom ends. The bottom begins to matter. The wave slows from below. The crests draw closer. The height increases. The front face grows steeper. And the wave that once rolled smoothly through open water begins to lean forward as if the top is trying to keep going while the base is held back. That imbalance cannot last forever. That imbalance becomes the breaking wave, The lower part of the wave is slowed by shallow water. The upper part keeps moving forward. For a while, the wave can hold its shape. It rises taller. Its front face steepens. Its crest becomes thinner and sharper. Then the top begins to outrun the base. At that moment, the wave is no longer stable. The water at the crest has nothing firm beneath it to support the forward motion. Gravity takes over. The lifted water falls. The crest spills, plunges, or collapses into the trough ahead. That falling motion is what creates the familiar crash of surf. It is not just a wave ending. It is energy being released. A breaking wave mixes water and air together. That is why the clean blue or green face suddenly turns white. The white part is foam, and foam is full of bubbles. Each bubble is a tiny pocket of air wrapped in a thin film of water. When thousands or millions of bubbles form at once, the surface becomes bright, frothy, and noisy. Some bubbles pop quickly. Others are pulled back into the next wash of water. Together, they create the soft hiss and fizz that trails after the heavier crash. Different waves break in different ways. A spilling breaker is gentle and gradual. The crest crumbles down the front of the wave, making a long line of whitewater. These often form on flatter beaches where the seafloor rises slowly. A plunging breaker is steeper and more dramatic. The crest curls forward and falls into open air before striking the water below. These can form where the bottom rises more suddenly, such as over a reef, sandbar, or steeper beach. A surging breaker may not fully curl at all. Instead, the wave rushes up a steep shoreline with a strong sliding push. The type of breaking wave depends on the slope of the seafloor, the wave's height, and the wave's length. The shore shapes the break before the eye ever sees the foam. This is why two beaches can sound and look so different. On one beach, waves may pour forward in soft white lines for many seconds. On another, they may rear up quickly and strike the sand with a deep, hollow thud. The same ocean can whisper in one place and pound in another, simply because the bottom is shaped differently. Surfers often describe a wave as hollow, mushy, fast, slow, heavy, or gentle. Those words may sound casual, but they are really descriptions of physics. A hollow wave has a steep face and a curling crest. A mushy wave breaks slowly because its energy is spread out. A heavy wave has more power packed into a shorter space. Each feeling comes from height, period, bottom shape, and speed all meeting at once. Breaking also changes the movement of water near shore. When a wave collapses, water rushes forward a swash. Swash is the sheet of water that runs up the beach after a wave breaks. Then gravity pulls it back down as backwash. That back and forth motion carries sand, shells, seaweed, and tiny stones with it. A single small wave may move only a thin layer of grains. But waves do not arrive once. They arrive all day, all night, in winter storms, in summer calm, under moonlight, under cloudy morning skies. A typical beach can receive thousands of breaking waves in a single day. Each one spends a little energy on the shore. Each one moves material, stirs bubbles, shifts sand, and changes the line where land and water meet. From far away, the sound can feel soft and steady. A low breath, a hush, a gentle crash followed by a retreating whisper. But close up, that sound is made by moving mass, by falling water, by air forced into foam, by sand dragged across sand, by gravity pulling water downhill toward the sea. The breaking wave is the place where ocean energy becomes visible, audible, and touchable. It is where a distant wind finally spends part of what it gave to the water. And once that energy reaches the shore, it does not simply vanish. It presses against rock. It lifts sand. It enters cracks. It carries pieces away. The crash fades. The foam thins. The beach grows quiet for a moment. Then the next wave arrives, and the slow work begins again. The slow work begins with contact. A wave reaches land and spends its energy against whatever is waiting there. Sometimes that is soft sand. Sometimes it is loose gravel. Sometimes it is a wall of stone, rising straight from the sea. Along rocky coasts, waves can strike cliffs with surprising force. During storms, large breaking waves can hit with enough pressure to shake loose blocks of rock, widen cracks, and send spray high into the air. The process is not always fast. A cliff may look solid for decades, but waves keep returning. They press water into tiny gaps. They force air into cracks. Then, when the wave pulls back, the pressure changes again. This repeated squeezing and releasing is called hydraulic action. Hydraulic simply means it involves water pressure. Over time, hydraulic action can weaken rock from the inside, especially where cracks, joints, or softer layers already exist. The wave does not need to break the whole cliff at once. It only needs to loosen one piece, then another, then another. Water also carries tools with it. Sand, pebbles, and broken shells can be lifted by waves and thrown against rock. This is called abrasion. Abrasion means wearing something down by rubbing or scraping. It is similar to sandpaper smoothing wood, except the ocean sandpaper is made of moving sediment. A pebble rolled again and again at the base of a cliff can help grind the rock. A storm wave filled with gravel can strike like a rough brush, scraping the surface and widening weak spots. This is one reason sea caves can form. Waves attack a softer part of a cliff. The opening grows. The cave deepens. If waves keep working from both sides of a headland, the cave may eventually become an arch. Later, if the arch roof collapses, a tall pillar of rock can be left behind. That pillar is called a sea stack. Places like the 12 Apostles along the coast of Victoria, Australia, show this process clearly, with limestone stacks standing offshore where cliffs were slowly cut back by waves, wind, and weather. But waves do not only destroy, they also build. The same water that removes sand from one place can drop it somewhere else. When wave energy weakens, heavier pieces settle first. Pebbles fall. Coarse sand settles. Finer grains may travel farther before sinking. This is how beaches can form. A beach is not just a pile of sand beside the sea. It is a temporary storage place for broken rock, shell fragments, coral pieces, and mineral grains. On many beaches, the sand is mostly quartz, a hard mineral that survives long travel by rivers and waves. On tropical islands, sand may include crushed coral, bits of sea urchin spine, tiny shell fragments, and the remains of marine organisms. In Hawaii, some beaches are black because the sand comes from volcanic basalt. In Bermuda, some beaches look pink because they contain pieces of tiny red-shelled organisms mixed with pale sand. Each beach is a record of what the waves have been given to carry. Cliffs, rivers, reefs, volcanoes, shells, and old seafloors can all become part of the shore. This makes a coastline less like a fixed border and more like a living edge. Maps draw it as a line, but in real life, that line is always being adjusted. A winter storm can pull sand offshore in a single night. Gentler summer waves can bring some of it back over weeks or months. A beach that looks wide and soft in August may look narrow and steep after a strong storm in January. Barrier islands, sandbars, dunes, and spits can shift as waves move material along the coast. The land and sea are constantly trading pieces. A grain of sand may be lifted, dropped, buried, uncovered, and moved again many times. It may travel along the same beach for years. It may be pulled offshore during a storm and return during calmer weather. It may rest for a while beneath someone's footprints, then be carried away by the next tide and wave. So the soft crash of surf is not only sound, it is work. It is pressure against stone. It is sand sliding over sand. It is broken shell becoming beach. It is the shore slowly changing shape under the steady touch of moving water. And even when the beach looks quiet, even when the surface seems still between waves, the sand beneath that calm edge is often already on its way somewhere else. Some of that sand does not move straight in and straight out. It travels sideways. A beach may look like a quiet strip between land and sea, but wave after wave can slowly slide its grains along the coast. This happens because waves do not always arrive straight toward shore. Very often, they approach at an angle. A swell may come from the northwest. A local wind wave may arrive from the southeast. The shape of the coastline may bend the waves before they break. By the time the water reaches the beach, it may be moving diagonally across the sand. When a wave breaks at an angle, the swash runs up the beach at that same angle. Swash is the thin sheet of water that rushes forward after a wave breaks. It carries sand grains with it. Then gravity pulls the water back down the beach. That returning water is called backwash. But backwash usually flows more directly downhill toward the sea. So each wave gives sand a small sideways step. Up the beach at an angle. Back down more directly. Up again at an angle. Back down again. The pattern is gentle, but it repeats thousands of times. The result is called longshore drift. Longshore means along the shore. Drift means slow movement. Together, the words describe sand being moved along a coastline by angled waves. A single grain may travel only a short distance with each wave. Maybe a few centimeters, maybe less. But over days, months, and years, the total movement can be enormous. Some coasts move thousands or even millions of cubic meters of sand each year through longshore drift. A cubic meter is about the space inside a large washing machine. Now imagine that amount repeated again and again, until the beach itself is quietly migrating. This is why a shoreline can change even without a dramatic storm. It does not need one huge event. It only needs steady waves arriving from a common direction. On many beaches, you can see small clues. Foam lines may slide diagonally. Bits of seaweed may move along the shore instead of straight back out. A small shell placed near the waterline may slowly shift down the beach with each wash of water. The motion is calm enough to miss, but constant enough to matter. Longshore drift helps create some beautiful coastal shapes. A spit, for example, is a narrow finger of sand or gravel that grows out from land into open water. It forms when longshore drift carries sediment along a coast and deposits it where the shoreline changes direction or where wave energy weakens. Spurn Head in eastern England is one well-known example. A curving strip of sand and shingle reaching into the mouth of the Humber estuary. Barrier islands can also be shaped by waves moving sand along shore. These long, low islands stand between the open ocean and quieter bays or lagoons. Along the Atlantic and Gulf coasts of the United States, barrier islands shift under the influence of waves, tides, storms, and sea level change. They may look fixed from a road or a map, but they are made of mobile sand. The ocean is always sorting and moving them. This sideways motion can create problems when humans build near the water. A harbour entrance, jetty, seawall, or breakwater can interrupt the natural movement of sand. If a structure blocks longshore drift, sand may pile up on one side. On the other side, the beach may be starved of new sediment and begin to shrink. The waves keep arriving. The sand keeps trying to move, but the pathway has been changed. This is one reason coastal engineering is so difficult. Protecting one stretch of shore can sometimes make erosion worse somewhere nearby. A beach is connected to the beaches beside it. A grain removed from one place may have been part of the supply for another. The coastline is not a row of separate pieces. It is a moving system. Waves push, gravity pulls, sand shifts, and the shore slowly redraws itself in long, quiet lines. From far away, longshore drift is almost invisible. There is no roaring collapse, no cliff falling into the sea. Only thin sheets of water sliding across sand again and again. Yet this small diagonal motion can build spits, feed beaches, expose roots, uncover old rocks, and change the shape of harbours. The same waves that sound soothing at night are also organising the coast grain by grain. And because sand moves, people have learned to build, defend, redirect, and sometimes fight against the shore itself. People have been trying to calm waves for thousands of years. Anywhere boats needed to rest, unload, or return safely. Waves became more than a sound. They became a problem to solve. A fishing boat can handle gentle motion while it is moving. But tied to a dock, even small waves can make ropes strain, hulls bump, and cargo shift. A harbour needs water that is deep enough for vessels, but quiet enough for people to work. So humans began shaping the edge of the sea. One of the oldest tools is the breakwater. A breakwater is a wall or barrier built offshore or near a harbour entrance to reduce wave energy. It does not stop the ocean completely. It simply takes part of the wave's force before the water reaches the sheltered side. When a wave hits a breakwater made of stone blocks, concrete, or piled rock, some energy is reflected back seaward. Some is spent in turbulence. Some is broken into smaller, weaker waves. Behind the barrier, the harbour water becomes calmer. Ancient harbour builders understood this long before modern engineering. The Romans built large harbour structures using a type of concrete that could harden underwater. At Caesarea Maritima, on the coast of present-day Israel, King Herod's engineers built a huge artificial harbour around 22 to 10 BCE. They used volcanic ash in their concrete, which helped it set in seawater. The goal was simple and difficult at the same time. Create a safer pocket of water along an exposed coast. The same idea continues today. Modern breakwaters may be made of rock, concrete caissons, or specially shaped armor units designed to lock together. Some look like great piles of grey stone stretching into the sea. Others sit just below the surface, hidden except when waves rise over them. But their purpose remains the same. They interrupt the wave before it spends all its energy on the shore or inside the harbour. Seawalls work differently. A seawall is usually built along the land itself, often at the back of a beach or in front of roads, homes, or boardwalks. Instead of letting the wave spread slowly inland, the wall gives it a hard surface to strike. This can protect what sits behind it, but it can also reflect energy back toward the beach. That reflected force may pull sand away from the base of the wall. Over time, the beach in front can become narrower. The wall protects the land behind it, but the beach itself may lose room to move. Dunes and wetlands handle waves in a softer way. A sand dune does not stand like a solid wall. It absorbs energy by changing shape. During a storm, waves may cut into the front of a dune and carry sand away. That sounds destructive, but the dune is doing part of its job. It gives up sand so the force does not reach farther inland as easily. Coastal wetlands, marshes, mangrove forests, and seagrass beds can also slow water down. Their plants create drag, which means they resist the motion of moving water. In places with mangroves, the tangled roots can reduce wave energy and trap sediment. Salt marsh grasses bend with the water, slowing waves while helping hold muddy shorelines together. This is why many coastal planners now think about natural protection as well as hard structures. A concrete wall may be strong, but a living shoreline can absorb, flex, and repair itself over time. Still, every choice changes the movement of sand and water. A jetty built to keep a harbour entrance open may trap sand on one side. The beach on the other side may erode. A breakwater may calm one stretch of water, while changing wave patterns nearby. A seawall may protect buildings while leaving the beach below thinner year after year. The sea is connected. Push against it in one place, and the effect may appear somewhere else. This is what makes waves so hard to control. They are not single objects arriving alone. They are part of a wider system of wind, swell, tides, currents, sand, rock, and shoreline shape. Humans can guide them for a while. We can weaken them, reflect them, absorb them, make quiet harbors where ships can sleep at anchor. But outside those sheltered waters, the waves continue moving. Beyond the breakwater, the open sea still rises and falls. And any vessel leaving the calm harbor mouth must meet the ocean on its own terms. Outside the harbor, the ship enters a different kind of conversation with the sea. The waves are no longer something heard from land. They are something felt through wood, steel, rope, glass, and bone. A vessel does not simply sit on top of the ocean. It answers every rise and fall beneath it. A small wave may lift the bow. A second wave may roll under the middle. A third may strike from the side and tilt the deck just a little. Even a large ship is always responding. It is being carried, lifted, lowered, pushed, and turned by repeating motion. For anyone traveling by sea, wave height matters. A 1-meter sea may feel mild on a large ferry. A 3-meter sea can make walking difficult on a smaller boat. A 6-meter sea can become serious even for trained crews, especially if the waves are steep or coming from an awkward direction. But height is only part of the story. A wave's period can matter just as much. A 2-meter wave arriving every 5 seconds may feel sharp and uncomfortable. The boat barely has time to settle before the next crest arrives. It may slap into the hull again and again, making the ride rough, noisy, and tiring. A 2-meter swell arriving every 14 seconds can feel much smoother. The vessel rises slowly. It reaches the top. Then it settles gently down the back. The height may be the same, but the motion feels completely different. This is why sailors often care about wave period, not just wave height. A short period sea is like a bumpy road with closely spaced potholes. A long period swell is more like rolling over wide hills. The ship has time to adjust. The body has time to feel the motion and prepare for the next rise. Wave direction also changes the journey. When waves come from ahead, the bow lifts and falls into them. This can slow the vessel down and send spray across the deck. When waves come from behind, the boat may slide down the front of each wave, sometimes gaining speed before the stern lifts again. When waves come from the side, the vessel may roll. Roll is the side-to-side motion, when one side of the ship rises and the other side lowers. Pitch is the front-to-back motion, when the bow and stern rise and fall. These motions are normal at sea, but their strength depends on how the ship meets the waves. A long ship crossing short waves may bridge over some of them. The bow and stern may be supported at the same time, making the motion less severe. But if the spacing between waves lines up badly with the ship's length, the motion can feel stronger. One crest may lift the bow, while another lifts the stern, leaving the middle less supported. Or the ship may drop into a trough, while the next crest rises ahead. This relationship between ship size and wave spacing is one reason the same ocean can feel different on different vessels. A kayak, a fishing boat, a ferry, and a cargo ship each read the sea in their own way. A wave that feels large to a kayak may be barely noticed by a container ship. A short, steep chop that shakes a small boat may feel like a light vibration on a large vessel. But even the largest ships are not separate from the waves. Modern container ships can be more than 300 meters long. Some oil tankers are even longer. They are enormous compared with most waves near shore. Yet in the open ocean, long swell can also stretch hundreds of meters from crest to crest. At that scale, the ship and the wave begin to meet as large systems. Steel bends slightly. Cargo must be secured. Engines work harder in head seas. Crews adjust speed and course to reduce strain. Navigation is not only about steering from one point to another, it is also about choosing how to meet the sea. Sometimes a captain changes course slightly to take waves at a safer angle. Sometimes a ship slows down so it does not slam into the next crest. Sometimes it waits for a storm system to pass, because the cost of forcing a vessel through heavy seas can be damage, delay, or danger. The ocean surface may look open, but it is not empty. It is full of moving shapes. Some are gentle, some are steep, some are spaced wide apart, some arrive too quickly, and every vessel leaving sheltered water must find its rhythm among them. The wave lifts, the hull answers, the deck tilts, the motion repeats. And with enough time at sea, it becomes clear that travel over water is never perfectly still. It is a constant negotiation with energy passing beneath the ship. That negotiation happens through the body of the ship. Every vessel has its own way of moving. A small boat may respond quickly, lifting and turning with each passing wave. A heavy cargo ship moves more slowly, with thousands of tons of steel resisting each rise and fall. But all ships are shaped by the same basic motions. Pitch is the front-to-back movement. The bow rises, the stern lowers. Then the bow drops again as the ship settles into the next trough. From the side, the ship looks as if it is gently nodding. Roll is the side-to-side movement. One side of the vessel lifts, the other side dips. Then the motion reverses. On deck, this can make the horizon tilt left and right, like a slow-moving line across the sky. There is also heave, which is the whole ship moving up and down. Surge, which is forward and backward motion. Sway, which is side-to-side motion. And yaw, which is the ship turning slightly left and right around its center. Together, these are often called the 6 degrees of motion. They describe the main ways a vessel can move in 3-dimensional space. For someone trying to sleep in a cabin at sea, the names may not matter, but the feeling does. A gentle pitch can feel like being rocked. A slow roll can feel almost calming if the movement is even. But sharper motion can make the body work harder to keep balance. The inner ear, where the body senses motion and position, notices every tilt. This is one reason seasickness can happen. The eyes may see a quiet wall or cabin ceiling, but the inner ear feels the ship moving. When those signals do not match, the body can become confused. The direction of the waves makes a great difference. Head seas come from ahead. The bow meets the waves first. It climbs the front of each crest, then drops down the back. In steep head seas, the bow can slam into the next wave, sending a heavy vibration through the hull. Following seas come from behind. The waves lift the stern and push the vessel forward. This can feel smoother in some conditions, but it can also become tricky if the ship starts sliding down the front of a wave too quickly. Beam seas come from the side. These often create more roll because the waves lift one side of the vessel before the other. A boat in beam seas may rock left and right again and again, with cups sliding on tables and ropes creaking against cleats. Quartering seas come at an angle from behind or ahead. They can combine pitch, roll, and yaw in a more uneven pattern. This is why captains do not only ask how high the waves are, they also ask where the waves are coming from. A 3-meter sea from ahead may feel very different from a 3-meter sea from the side. The ship's shape matters too. A wide vessel often resists rolling better than a narrow one. A deep keel can help steady a sailboat. Modern passenger ships may use stabilizers, which are fin-like structures that extend from the hull and push against the water to reduce roll. Some stabilizers can adjust automatically as sensors detect the ship's movement. They do not stop the sea. They simply help the ship answer it more smoothly. Yet even a stable ship has a natural rhythm. Every vessel tends to roll or pitch at certain rates, depending on its size, shape, weight, and how its cargo is loaded. This is called its natural period. A small boat may have a quick natural period. A large ship may have a slower one. If waves arrive in a rhythm that lines up with the ship's natural motion, the movement can grow stronger. This is called resonance. A gentle example is pushing someone on a swing. A small push at the right moment can make the swing go higher. A mistimed push does much less. Waves can affect a ship in a similar way. If the timing fits badly, each wave adds to the motion already happening. The roll becomes wider. The pitch becomes heavier. The ride becomes more tiring and less safe. So crews adjust. They may slow down. They may turn slightly. They may change how the vessel meets the waves so the motion becomes easier to manage. In ordinary seas, these choices can keep the journey steady enough. The ship lifts, tilts, settles, and continues. But storms do not always send waves in one clean rhythm. They can fill the water with crossing patterns, uneven timing, and steep shapes that refuse to behave like a simple rolling swell. That simple rolling swell can disappear inside a storm. The ocean surface becomes harder to read. Instead of one clean set of waves moving in one direction, several wave systems may exist at the same time. Some waves may be made by the strongest winds near the center of the storm. Others may have been created hours earlier, when the wind blew from a different direction. Older swell may still be moving through from another weather system far away. All of these patterns can overlap. The result is often called a confused sea. A confused sea does not mean the water has no rules. It means too many rules are acting at once. One wave train may move from the west. Another may move from the south. A shorter local chop may be pushed across the surface by wind blowing from the northwest. Each set has its own height, period, speed, and direction. When they meet, the sea stops looking like a neat row of lines. It becomes uneven. Crests rise at odd angles. Troughs appear where the water was lifting a moment before. The surface can look crossed, wrinkled, and broken, like several invisible hands are moving the same sheet in different directions. In meteorology, people often describe the state of the ocean using sea state. Sea state is the overall condition of the surface based on wave height, wind, and roughness. A calm sea may have almost no visible waves. A moderate sea may have whitecaps and rolling motion. A storm sea can have large, steep, irregular waves with foam blown into streaks. On the Beaufort scale, storm force begins around 48 knots of wind At those speeds, the sea surface is covered with foam. Spray reduces visibility, and waves can become high enough to hide parts of the horizon from a small vessel. But the height alone does not explain the difficulty. The shape matters. A long swell may lift a vessel smoothly. A short, steep wave can strike it sharply. In storms, waves often become steeper because strong wind keeps feeding energy into the surface. If the wind changes direction quickly, the new waves may run across the old ones. This creates crossing seas. Crossing seas happen when two or more wave systems meet at an angle. From above, they can make the ocean look like a moving grid. Near Ile de Ré, off the west coast of France, crossing wave patterns are sometimes visible when swell and local waves meet in shallow water. The surface forms diamond-like shapes, beautiful from a distance, but uneasy for boats because the motion comes from more than one direction. A vessel in crossing seas may pitch and roll at the same time. The bow rises into one wave while the side is lifted by another. The deck may tilt in a way that feels less predictable than simple swell. For crews, this makes movement more tiring. For cargo, it increases stress. For the ship itself, it changes how force travels through the hull. The ocean is still only water, but the timing has become complicated. Sometimes, overlapping waves cancel each other partly. A crest meets a trough, and the surface becomes lower than either wave would be alone. Other times, the waves add together. A crest meets another crest, and the water rises higher. This is called constructive interference. Interference simply means waves meeting and changing each other. Constructive means they build together. It can happen with sound, light, ripples in a pond, and ocean waves. In a storm sea where many wave patterns cross at once, moments of building can appear suddenly. Most of the time, the sea may stay within a rough but expected range. Then, for a few seconds, several crests may arrive in the same place. The water lifts higher than the surrounding waves. The face steepens. The trough ahead may be unusually deep. To a ship, that moment can feel very different from the average sea around it. This is why mariners do not judge the ocean only by what the last wave did. They watch the pattern. They watch the spacing. They notice whether the waves are lining up or crossing. They feel whether the sea has a steady rhythm or a broken one. Storms make this harder because wind, swell, current, and shifting pressure all right over each other. The surface becomes layered with old energy and new energy at the same time. A wave born hours ago may meet a wave born minutes ago. A long swell may pass through short local chop. A current may slow part of the wave field, making crests stand taller. The sea becomes a moving puzzle of force and timing. Most of these waves pass, break, and fade like the others. But when several pieces of motion meet in just the wrong place, at just the wrong moment, the ocean can rise into something far larger than the waves around it. Something far larger can appear without looking like a separate kind of sea at first. For centuries, sailors told stories of waves that seemed too large for the weather around them. A ship might be moving through heavy but manageable water. Then one wave would rise above the others, steeper, taller, stranger in shape. For a long time, these stories were treated as exaggerations. The ocean is difficult to measure from a ship in bad weather, and fear can make memory feel larger. But modern instruments change the story. Rogue waves are real. A rogue wave is usually defined as a wave more than twice the significant wave height. Significant wave height means the average height of the highest 1/3 of waves in a sea state. So if the significant wave height is 6 meters, a rogue wave would be more than 12 meters high. It is not just large. It is unusually large compared with the waves around it. One famous measurement came on January 1st, 1995, at the Draupner gas platform in the North Sea. In a sea where the significant wave height was about 12 meters, instruments recorded a single wave about 25.6 meters high. That is roughly the height of an 8-story building. It was not a legend. It was a number recorded by equipment fixed in the ocean. After that, scientists took rogue waves much more seriously. Ships, satellites, buoys, and offshore platforms have since shown that these sudden giants can happen in real seas. They are uncommon, but not impossible. They are part of the ocean's range of behavior. A rogue wave can form in more than one way. Sometimes ordinary waves overlap at the right moment. Several crests meet in the same place, and their heights briefly add together. This is constructive interference, the same idea that lets ripples in a pond build a higher peak when they cross. Most of the time, the meeting is small and temporary. But in a stormy sea, with many wave systems moving through each other, the combined crest can become much larger than nearby waves. Currents can also help create extremes. When waves travel against a strong current, their energy can become compressed. The waves slow down. Their crests bunch closer together. Their height can increase. This is one reason places with strong currents and storm waves can be especially dangerous. The Agulhas Current off South Africa is one well-known example. It flows along a major shipping route, where powerful waves from Southern Ocean storms can meet fast-moving current. When wave energy is squeezed into a smaller space, the sea can become steeper and less predictable. Storm patterns can focus energy too. A large storm is not a perfect circle of wind. It has shifting bands, pressure changes, and areas where wind pushes more strongly in one direction. If those winds keep feeding a wave field while the waves move with the storm, energy can gather into larger waves. The sea becomes organized in a dangerous way, not smooth and calm, but focused. A rogue wave may also have an unusually deep trough in front of it. To a ship, this matters. The vessel may drop lower than expected, then meet a steep wall of water rising ahead. Even if the wave lasts only seconds, those seconds can place tremendous force on the bow, deck, windows, containers, or equipment. This is why rogue waves are not only about height. They are about steepness, timing, and surprise. A long swell gives a ship time to rise. A sudden steep wave can meet the vessel like a moving cliff. From a distance, the idea of a rogue wave may sound dramatic, but scientifically, it belongs to the same family of wave behavior already unfolding beneath the surface. Wind adds energy. Waves travel. Waves overlap. Currents reshape them. Storms focus them. Most of the time, These processes create ordinary rough seas. Once in a while, the timing becomes unusual enough for the ocean to lift into a rare extreme. That makes rogue waves both startling and understandable. They are not magic. They are not outside nature. They are nature briefly arranging its motion in a powerful way. A crest meets a crest. A current tightens the spacing. A storm keeps feeding the pattern. The sea rises higher than expected, then falls back into the restless surface around it. And still, some of the ocean's most dangerous waves do not begin with wind at all. They begin when the seafloor itself moves. A tsunami is not the same kind of wave as the wind waves we have been following. It does not usually begin with air dragging across the ocean. It begins when a huge amount of water is suddenly pushed out of place. Most tsunamis are caused by undersea earthquakes. These happen where pieces of Earth's crust, called tectonic plates, press against each other beneath the ocean. If one plate suddenly slips upward or downward, the seafloor can jump. When the seafloor moves, the water above it must move too. The ocean surface may lift or drop across a wide area. Then gravity tries to pull the disturbed water back into balance. That motion spreads outward as a tsunami. The word tsunami comes from Japanese and means harbor wave. It is a fitting name because these waves may be hard to notice in deep water, but become dangerous near harbors and coasts. In the open ocean, a tsunami may be less than a meter high. A ship, far offshore, might pass over it, without seeing anything dramatic. There may be no curling crest, no white foam line, no tall wall of water crossing the horizon. But its shape is enormous. A normal wind wave might have a wavelength of 100 or 200 meters. A tsunami can have a wavelength of 100 kilometers or more. That means the distance from one crest to the next can be longer than an entire city, longer than a mountain range, longer than the drive between many towns. Because the wave is so long, it reaches all the way down through the ocean. Unlike ordinary surface waves, which fade with depth, a tsunami involves the full water column from surface to seafloor. In deep water, tsunamis can move extremely fast. Some travel at speeds around 700 to 800 kilometers per hour, similar to a passenger jet. The speed depends on water depth. The deeper the ocean, the faster the tsunami can move. Across the deep Pacific, a tsunami can cross thousands of kilometers in a matter of hours. Yet from above, the open ocean may still look strangely calm. The danger is hidden in the length of the wave, not in a towering shape far offshore. Everything changes near land. As the tsunami reaches shallower water, the lower part of the wave feels the seafloor. It slows down, but the energy behind it keeps arriving. The wavelength shortens. The water piles upward and forward. This is called shoaling, the same basic process that makes ordinary waves rise near shore, but on a much larger scale. A tsunami does not always arrive as one clean breaking wave. Often, it looks more like a rapid rise of the sea. Water may pull away from the beach first, exposing rocks, sand, or reef that are normally covered. Then the ocean may return as a fast, powerful surge. The flooding can continue for many minutes, and there may be more than one wave. The first arrival is not always the largest. In the 2011 Tohoku tsunami in Japan, caused by a magnitude 9.0 undersea earthquake, waves traveled across the Pacific and were measured as far away as North and South America. The event showed how a movement in one part of the seafloor can send energy across an entire ocean basin. That is the deeper lesson inside a tsunami. A wave is not defined only by what it looks like on the surface. A small-looking motion in deep water can hold immense energy if it is long enough, fast enough, and connected to enough moving water. The ocean does not need a high crest to carry power. Sometimes the power is spread quietly over a vast distance. This makes tsunamis very different from the relaxing waves at the beach, but they still reveal the same core truth. A wave is energy moving through water. Wind can create that energy. Gravity can shape it. The seafloor can release it, and the coast can transform it. The same principle appears again and again, from a tiny ripple to a basin-wide surge. Water rises, energy travels, the shape changes as depth changes. And once waves are understood this way, they stop seeming like simple surface motion. They become moving stores of energy. Some of that energy is dangerous and must be respected. But some of it is steady, repeating, and always arriving. The sea lifts, falls, and lifts again. And quietly, beneath that motion, there is a possibility humans have been trying to understand for generations. Can the restless movement of waves be turned into power? The restless movement of waves can be thought of as stored motion, not stored in one place like water behind a dam, but carried again and again through rising, falling, tilting, and forward pressure. Every wave contains mechanical energy. Mechanical energy simply means energy connected to motion or position. When the water lifts upward, it has energy because gravity can pull it back down. When the water moves forward and backward beneath the surface, it has energy because moving water can push against something. A wave is both lifted water and moving water. That is why it can rock a boat, shift sand, break against a wall, or turn a floating object again and again. The energy is not locked inside the water like fuel inside a tank. It is in the pattern of motion. The crest rises, the trough lowers, the surface tilts, the water below moves in loops. Then the pattern passes onward. This repeating motion is what makes wave energy so interesting. A single wave is brief. It arrives, lifts, breaks, and fades. But the ocean does not send only one wave. It sends thousands. Along some coastlines, waves arrive every few seconds for most of the year. If a wave period is 10 seconds, then 6 waves can pass in 1 minute. That is 360 waves in 1 hour. More than 8,000 in a day. Even if each wave is modest, the repetition adds up. The sea is patient with its energy. It does not spend everything in one moment. It gives motion in steady pulses. Wave energy also has a useful difference from sunlight. Solar power depends on daylight. At night, the panels wait. Clouds can reduce the energy reaching them. Waves are different. They can keep arriving in darkness. A swell born from a faraway storm may reach a coast under a clear night sky long after sunset. The water does not care whether the beach is bright or dark. It rises because energy is already moving through it. Wave energy is also different from local wind. A wind turbine depends on wind blowing where the turbine stands. But ocean swell can arrive from weather hundreds or thousands of kilometers away. The air above the coast might be calm. The sea may still lift and fall because a storm far offshore sent motion toward land days earlier. That makes waves a kind of delayed energy from weather. The wind works in one place. The ocean carries the result somewhere else. Some coastlines receive more of this energy than others. Western-facing coasts in the middle latitudes are often strong candidates because they face long stretches of open ocean. The west coast of Scotland receives energetic North Atlantic waves. Portugal faces swell from the Atlantic. Parts of Chile, New Zealand, southern Australia, and the Pacific coast of North America receive wave energy from large ocean basins. These places have long fetch, frequent storms offshore, and coastlines exposed to open water. In wave energy studies, the resource is often described in kilowatts per meter of wave crest. That means how much power is moving along each meter of wavefront. A calm sea may hold only a small amount. A strong open ocean swell can carry tens of kilowatts per meter. During storms, the number can grow much higher, though storm energy is also harder and more dangerous to capture. This is one of the central challenges. The ocean offers energy, but it does not offer it politely. The same coast that gives steady swell on an ordinary day may receive violent waves during winter storms. A machine built to harvest waves must be sensitive enough to use gentle motion, but strong enough to survive extremes. It must move with the sea without being torn apart by it. Still, the idea is beautiful in a simple way. The ocean is already lifting, already falling, already pressing forward and pulling back, already sending energy through water day and night. For centuries, people watched waves as obstacles, warnings, rhythms, and scenery. But the same motion that rocks a ship or carves a beach could also move a generator. The wave rises. A machine could rise with it. The wave falls. A machine could fall with it. The water pushes air, turns a joint, lifts a buoy, or bends a floating body. And somewhere inside that movement, electricity could begin. The energy is there. It has always been there. The difficulty is building something quiet, strong, and clever enough to receive it. To receive wave energy, a machine must first learn a simple lesson. It cannot pretend the ocean is still. It has to move. It has to rise, fall, bend, breathe, or turn with the water around it. One of the simplest ideas is a floating buoy. A buoy is a floating object anchored in place. When a wave passes, the buoy rises on the crest and falls into the trough. That up and down motion can be connected to a generator. A generator is a machine that turns movement into electricity, usually by moving magnets and coils of wire past each other. The wave lifts the buoy. The buoy pulls on a cable or piston. The motion turns part of the generator. Then the wave lowers the buoy, and the cycle begins again. The same kind of rise and fall that gently lifts a seabird can, in theory, help produce power. Some devices are called point absorbers. They are called that because they gather energy from one point on the sea surface. They do not need to stretch across a whole coastline. They sit in the water, moving with the waves around them. A group of them could be placed offshore like a quiet field of floating machines. Each one would harvest a small part of the ocean's repeating lift. Another design uses air instead of a floating body. This is called an oscillating water column. Oscillating means moving back and forth. Picture a hollow chamber built into the shore, or set offshore, with an opening below the waterline. As a wave enters the chamber, the water level inside rises. That rising water pushes air upward through a turbine. A turbine is a set of blades that spins when air or water moves through it. Then, as the wave falls away, the water level inside the chamber drops. Air is pulled back down through the turbine again. The air moves both ways. The turbine is designed to keep turning. The wave itself never has to touch the generator directly. It only has to move the water level up and down, like a slow ocean-powered lung. Some wave energy machines are longer and more flexible. They are built in sections joined together by hinges. As waves pass beneath them, the sections bend. One part rises while another part lowers. The hinge between them moves, and that motion can drive hydraulic pumps or generators. Hydraulic means using liquid under pressure to move force from one place to another. These devices are sometimes compared to sea snakes because they float in long linked bodies across the water. The idea is to let the machine flex with the wave instead of standing stiff against it. A stiff object may be punished by the sea. A flexible one may survive by yielding. Other systems use flaps fixed to the seabed in shallow water. When waves move back and forth near the bottom, the flap swings like a door. That swinging motion can pump fluid or turn machinery. These devices are designed for the surge of water under waves, not just the rise and fall at the surface. They show that wave energy is not only above the waterline, it is also in the push and pull below. All of these designs share the same goal. Take repeated ocean motion and convert it into a steadier flow of electricity. The wave is irregular. The grid needs power that is controlled. So the machine must smooth the motion, protect its parts, and send energy through cables back to shore. In some test projects, underwater cables carry electricity from offshore devices to land-based equipment. From there, the power can be adjusted and added to the electrical grid. The idea sounds calm when described slowly. A buoy rises, a chamber breathes, a hinge bends, a flap swings. Each motion follows the sea instead of fighting it. But the ocean is not a laboratory tank. It is saltwater, storms, currents, marine growth, drifting debris, and constant force. A machine may work beautifully in a small test pool. Then the real ocean asks a harder question. Can it keep working through years of waves, winter storms, corrosion, and repair? The real ocean is patient, but it is not gentle with machines. A wave energy device may look simple in a drawing. A buoy rises, a hinge bends, a chamber fills and empties. But every part has to survive in seawater. And seawater is one of the most difficult environments on Earth for metal, wires, seals, bearings, and moving joints. Salt water causes corrosion. Corrosion is the slow chemical damage that happens when materials react with their surroundings. Iron and steel can rust. Aluminum can pit. Even strong alloys can weaken if salt water finds the right crack or scratch. The ocean also carries oxygen, minerals, sand, and tiny living things. Barnacles, mussels, algae, and other marine life can grow on submerged surfaces. This is called biofouling. A smooth metal part can become covered in rough living layers. A sensor can be blocked. A moving joint can become harder to move. A cable can collect growth that adds weight and drag. So a wave energy machine is not only fighting waves, it is living in a wet, salty, biological world that slowly tries to cover and wear down everything placed inside it. Storms add another problem. A device built to harvest ordinary waves must also survive rare extreme ones. On a calm day, a buoy may rise and fall by 1 or 2 meters. During a powerful storm, waves can be many times higher, steeper, and more chaotic. A machine that is too light may be damaged. A machine that is too heavy may be too expensive or too slow to respond to smaller waves. This creates a difficult balance. The device must be sensitive enough to capture gentle motion, but strong enough to endure violence. It is like asking a watch to survive inside a washing machine for years. The ocean never stops moving. Even when the weather looks calm, parts are flexing, pulling, rubbing, and vibrating. Over months and years, that repeated stress can cause fatigue. Fatigue means small damage building up after many cycles of force. A metal part may survive 1 wave easily. It may survive 1,000 waves. But after millions of waves, tiny cracks can begin. A wave period of 10 seconds means more than 3 million wave cycles in a year. For a machine offshore, repetition is not a small detail. It is the main condition of life. Maintenance is hard too. If a wind turbine on land needs repair, a crew can drive to it. If a solar panel needs cleaning, someone can reach it from the ground or a roof. But a wave energy device may sit offshore in rough water. Reaching it may require a boat, calm weather, trained divers, remotely operated vehicles, or heavy lifting equipment. A repair that would be simple on land can become expensive at sea. Bad weather can delay work for days or weeks, and the farther the device sits from shore, the harder everything becomes. Then there is the problem of electricity itself. A machine may create power in the water, but that power still has to reach land. Underwater cables must carry electricity from the device to shore-based equipment. Those cables must be protected from waves, anchors, fishing gear, shifting sand, and corrosion. Once the power reaches land, it must be adjusted to match the electrical grid. The grid needs stable electricity at the right voltage and frequency. But waves are irregular. A calm set may pass. Then a stronger set arrives. Then a pause, then a storm. The machine must turn that uneven motion into usable power. This does not make wave energy impossible. It makes it demanding. The resource is enormous because the ocean is always receiving energy from wind, storms, and gravity. Many coastlines receive waves day after day, season after season. Unlike a single fuel tank, the ocean does not empty after one use. The motion keeps returning, but harvesting it requires patience. Materials that resist salt, designs that bend without breaking, systems that can shut down safely during storms, cables that can survive underwater, and maintenance plans that accept the sea as it is. Wave energy is promising because the ocean carries so much motion. It is difficult because that motion is never perfectly neat. The sea gives power impulses, sets, swells, storms, and quiet pauses. To use it well, humans cannot simply conquer the waves. They have to listen to their rhythm, build with their force in mind, and accept that the ocean always remains the larger partner. And at the shore, that truth becomes soft enough to hear. A wave arrives. It rises from the darker water. It folds into white foam. It runs up the sand in a thin, bright sheet. Then it slows, thins, and returns. At the beginning, that sound may have seemed simple. A calming crash, a gentle hiss, a rhythm for rest. But now the same sound carries more inside it. A beach wave is not only water touching land. It is wind made visible. It is gravity pulling lifted water back down. It is distance written into the spacing between crests. It is the seafloor shaping motion before the wave breaks. It is sand being moved grain by grain. It is the last form of energy that may have begun far offshore, under clouds no one on the beach ever saw. The ocean covers about 71% of Earth's surface. Across that wide blue space, air and water are almost always exchanging energy. Wind drags across the surface. Tiny ripples appear. Those ripples give the wind more texture to push. Waves grow with speed, time, and fetch. The open distance over which wind can blow. Then, when the storm fades, the water may continue carrying its pattern outward. A swell can cross thousands of kilometers. It can arrive under calm skies. It can lift a quiet shoreline long after its storm has disappeared. At the surface, a wave has a crest and a trough. It has height, wavelength, period, steepness, and direction. Beneath the surface, the water moves in looping paths that fade with depth. In deep water, the wave travels freely. Near shore, the bottom begins to guide it. The wave slows. Its crests crowd closer. Its height grows. Then the crest leans forward and falls. That falling water becomes the familiar break of surf. The sound that relaxes the body is also the sound of physics becoming audible. Air bubbles form and pop inside the foam. Sand grains scrape softly over one another. Water rushes forward as swash, then slides back as backwash. The beach is being touched, sorted, and remade. Cliffs are cut by pressure and abrasion. Shells are broken into sand. Dunes give up grains during storms and may receive them back in calmer seasons. Even a shoreline that appears still is often moving. A map may draw the coast as a clean line, but the real coast is a living edge. Waves also shape human journeys. A ship leaving harbor must meet height, period, direction, and steepness. It may pitch as the bow rises and falls. It may roll as waves lift one side and lower the other. In storm seas, wave systems can cross and combine. Sometimes the sea becomes confused, with old swell and new wind waves moving through each other. In rare moments, waves can join into sudden extremes. And in a different form entirely, a tsunami can cross deep ocean as a long, low movement of energy before rising near shore. All of these are waves, not because they look the same, but because they carry energy through water. That same idea also points toward the future. A wave can lift a buoy. It can push air through a turbine. It can bend a hinged machine. It can swing a flap near the seafloor. Turning that motion into electricity is difficult because salt water corrodes, storms damage, cables must survive, and the sea never moves in a perfectly even rhythm. But the possibility remains. The same rise and fall that rocks a boat and smooths a stone may also help power homes one day, if humans learn to build gently enough and strongly enough beside the ocean's force. So the wave returns to the shore with a different meaning now. It is still peaceful. It is still soft enough to fall asleep beside. But it is no longer empty background sound. It is a small, visible piece of Earth's larger exchange. Air pushing water. Gravity restoring balance. The seafloor shaping motion. Land receiving energy. Sand answering with movement. The planet is not still. It is always passing force from one form into another. And the wave is one of the gentlest ways to see that happening. A crest lifts. A trough follows. The foam spreads. The bubbles fade. The water slides back into the dark. And in that steady arrival and return, the ocean quietly reveals the physics of the whole planet.